We have an electron in between parallel plates as shown in the picture. There's uniform electric field pointing down. The electron is projected horizontally and it moves following a parabolic path. Why is it following a parabola? Because it goes sideways. So the horizontal motion is uniform. There's no acceleration in horizontal. There's just the initial horizontal velocity. And then in vertical, because there is vertical electric field, there's going to be a vertical net force on the electron pointing up in the opposite direction as the electric field. And that net force will create an acceleration upward. That's why the electron follows a parabolic path. And we are told that as it exits the region in between parallel plates, it just misses the end of the upper plate. So by the time the electron travels by delta x, the length of the plates, it also travels, that's in horizontal. In vertical, it travels half of the distance between the two plates, which I call delta y, as you can see in the picture. So what is it that's given? V0 is given, that's the initial velocity of my electron, that's the horizontal initial velocity. Delta x is given, the length of the plates, that's also the horizontal distance that the electron travels. Also, the distance between the two plates is given, that's 1 centimeter. That makes delta y 0.5 centimeters. So that's what I put on the board. What is it that we're trying to find? We're trying to figure out the strength of the electric field. So this is a multi-step problem. We're going to use kinematics equations to find the acceleration of the electron, and we're going to use the fact that net force equals mass times acceleration, that's Newton's second law for the electron, to find the electric field. Why? Because force is related to the electric field, right? So first thing first, how can I find the acceleration? I don't know much about the vertical motion. I know the vertical distance that the electron travels. I don't know how long it takes. I don't know the acceleration. So I need to know the time to find the acceleration, right? And to find the time, I can actually use the horizontal component of the motion. I know the horizontal velocity. I know the horizontal distance. This is uniform motion. There's no acceleration. So I can first find the time the electron takes to go one side of the place to the other side. So let's get started by setting up our equation for the horizontal motion. Delta x is equal to v naught x, initial horizontal velocity, which is basically the horizontal velocity, because the horizontal velocity doesn't change, times t, right? Times time, isolating time. T is equal to delta x divided by v0 x. So you can plug in the numbers and calculate. Delta x is 2 times 10 to negative second meters. V0x is the same thing as V0 because initial velocity is horizontal. That's 1.60 times 10 to the 6th meters per second. And when you plug in the numbers and calculate, here's what you get for time. 1.25 times 10 to the negative 8 seconds. So that's time. By the way, this is part A of the problem. Part A. There are other parts. Now that we know time, we can calculate acceleration. How do I do that? set up the kinematics equation for vertical position. Delta y is equal to v0y. This is accelerated motion in vertical times t plus 1/2 a sub y t squared. I'm looking for the vertical acceleration. I know delta y, I know t. What is v naught y? Well, that's 0 because initially the velocity is horizontal, so the vertical component of initial velocity is 0. So this first term is basically 0. Let's isolate the acceleration. Two times delta y divided by t squared. Again, if you plug in the numbers, here's what you get for the acceleration. 6.40 times 10 to the 13 meters per second squared. That's a pretty large acceleration. 10 to the 13 meters per second squared. Now that I know the acceleration, I can move on to Newton's second law to calculate electric field, basically. But how exactly? Well, there's net force. Well, what are the forces acting on the electron? Actually, there's gravity pulling down, electric force pushing up. Well, why is the electric force pointing up? Because this is an electron, electric field is pointing down. The force that the electron experiences must be pointing up, opposite the electric field direction. For reasons we will show later, Fg is much smaller than the electric force. So we're going to ignore Fg and we're going to say that F net is just the electric force. So F net y, so this is Newton's second law. F net y, actually let me just put a sigma sign here. So net force in the vertical direction is equal to mass, whose mass? The electron's mass, so m sub e, times the acceleration in vertical. And again, practically, all the force that we have in vertical is the electric force. That's the electric field strength times the electron's charge, elementary charge. Note that I'm not putting any negatives here because I know the direction of my force, so no need to put any negatives, don't need to have negative signs here. I'm just trying to find out this magnitude of the electric field. So the negative signs are irrelevant now that I have set up my force equation correctly. Just isolate the electric field. That's electron's mass, which is 9.11 times 10 to the negative 31st kilograms. And all the other, acceleration we calculated above. And the elementary charge is 1.60 times 10 to negative 19 coulombs. These are physical constants. You can look them up from a physics book. And here's the electric field strength that you would get when you plug in the values. (364). What's the unit? Newtons per coulomb. So that is the answer to part A. Now, part B is asking, if we had a proton instead of an electron, would the proton hit one of the plates? If not, calculate the vertical distance by which it travels. Now, let's think about it. So the proton is also projected with the same velocity. That means in horizontal, it's going to do the same thing because it's traveling by the same distance, delta x. So the time value for the proton will be the same. Now, what is going to be different for the proton? The proton has a different mass. How about the electric force? The electric force is going to be the same in terms of magnitude. Why? Because it's the same electric field, and magnitude-wise, it's the same charge. Electron and proton both have the elementary charge. One difference is that the force acting on the proton will be pointing down because it points in the same direction as the electric field. So the proton will also follow a parabolic path. This one is going to be curved downward. Now, the same electric force is acting on my proton, but the proton has a much greater mass, so it will have a smaller acceleration. Meaning in a given time interval, in the same time interval, in vertical, it will travel by a smaller distance compared to the electron. So by the time it exits the region in between the plates, it won't be able to reach the bottom plate because it has traveled less than half a centimeter, which is the distance that the electron was able to travel. So the answer is no, the proton is not going to hit the plate. That's the bottom plate. That's the direction in which it's moving. So it's going to make a curve, but it's not going to hit the plate by the time it exits the electric field region. So let's calculate the distance, the vertical distance by which it will travel. We need to recalculate the acceleration, this time from what we know from Newton's second law. So for the proton, we have the same magnitude of electric force. It's going to be equal to mass of the proton times a sub y. Now, I use a sub y for both, but this is the proton's acceleration, so it's going to be a different number. If you isolate acceleration and plug in the values for the electric field that we have already calculated, proton's mass is 1.67 times 10 to negative 27 kilograms. And here's the acceleration for the proton. 3.49 meters per second squared. Now we can go ahead and calculate the vertical distance by which the proton travels. Again, it is projected horizontally, so initially the vertical velocity is 0. Delta y is simply equal to 1/2 at squared for the proton. T is the same for the reason I explained. Again, when you plug in the values, you need to plug in the new value that we found for the acceleration, and t is the same, which is 1.25 times 10 to negative 8 seconds. So the answer here is going to be equal to 2.72 times 10 to negative 6 meters. Now, part C is asking about proton's path. Again, it's going to be a parabola, but it'll be less curved because in vertical the proton will travel by a smaller distance. And part D is asking if it makes sense to ignore gravity, which it does.